Hi everyone, this is Dr.S.SELVI, working as an associate professor in Erode Sengunthar Engineering College, Perundurai, Tamil Nadu. So today in this session, I am going to take few questions on recurrence relations. So we can go directly to the session. So in this recurrence relation, particularly, we are going to see about the Fibonacci series and also about the factorial of and factorial of a given number. How to generate the recurrence relation for a Fibonacci and a factorial number. Okay. So the question what will be asked regarding this, one of the format is, what is the generating function f of n for a sequence of Fibonacci series? Then, what is the time complexity of the generation of Fibonacci series? Right? So first one, which of the following recurrence relations can be used to find the nth Fibonacci number? So all of you know what is a Fibonacci number. So the Fibonacci number will be as such like, so it is similar to that of, so when it is 0 and take two numbers 0 and 1. So the next number what will be generated is 0 plus 1, it is 1. So now the next number what it will be generated is 1 plus 1, it is 2. So the next number what it will be generated is 1 plus 2, it is 3. So similarly, it will go till n, right? So for this problem, we have to find what will be the recurrence relation for this, right? Okay. So actually the answer for this is, so what we have done here is we have taken initially 0 and 1. So let us take 0 as A and 1 as B. So the next number what will be generated, let us assume as C. So C equal to A plus B. Now it is 1. Now next what we have to do is, so we have to take the first one as A and the second one, that is C, as B, and now we have to consider this as A plus A and B. Now C equal to A plus B, it is 1 plus 1, it's 2. Okay. Next, for the next term, we have to take A as A equal to 1 and B equal to 2, and now A plus B, it is equal to 3. So similarly, we have to generate till nth number. So now we have to look into how the factorial, how the recurrence relation for this equation can be generated. So actually how it can be generated is, so let us take f of n. So now we can take the third number as the f of n. Okay, so how the f of n will be generated? F of n equal to f of n minus 1 plus f of n minus 2. Let us take the third number 1 as n. Now the second number will be n minus 1 and the first number will be the n minus 2. So now f of n equal to f of n minus 1 plus f of n minus 2. So this will be the correct answer. The second question what you have seen here is, what is the time complexity for the generation of Fibonacci series? So for this, let us see how, how it will be generated. So I'll stop share this and I'll go with the another one PDF file. Yeah. So Fibonacci series. So how the algorithm can be generated is, so this is a recurrence relation. Recurrence relation is nothing but the same operation that can be repeated simultaneously, and how this can be executed by using functions. So here, as it is a recursive function, as it is a recursive, there is a recursive manner. We are going with the recursive functions. Actually, the recurrence relations can be generated for a recurable and a recursive problems or recursive operations. So now the Fibonacci can be generated either by using recursive or non-recursive. So, but the recurrence relation can be executed for for a recursive operation. So here we can go with algorithm fib of n. So we have to print the Fibonacci series. What will be the input? It will be the n. So what is the nth number to be generated? Output will be the Fibonacci number. Fibonacci number it is returned. If n is less than or equal to n, then it will be returning n. So if the nth value is less than 1, that is the input value is less than n, it will return you n, the same n. Else we'll be going with return a fib of n minus 1 plus fib of n minus 2. So using this algorithm, we can come to a conclusion that the formula for the nth Fibonacci number will be f of n equal to f of n minus 1 plus f of n minus 2. So now after simplifying it, we can go with f of n minus f of n minus 1 minus f of n minus 2 equal to 0. So now we have to derive we have to go with the solution for the second problem, that is what is the time complexity for a Fibonacci series. So for time complexity for a Fibonacci series, we have how it will be derived. So it can be derived in the following ways. So the characteristics equation for above equation can be, so it is in the format of r square minus r minus 1. So r square will be f of n, r will be f of n minus 1, and 1 will be f of n minus 2. So the above quadratic equation we can solve by finding out its roots. Now by using this Fibonacci, that is quadratic equation. So a will be, so what is the coefficient of all the terms? A will be 1, b will be minus 1, c will be minus 1. So actually how we can find out the roots of the quadratic equation by using the formula minus b plus or minus root of b square minus 4ac divided by 2a. So now the roots r1, r2 can be formulated by using the equation r1 equal to minus b plus root of b square minus 4ac divided by 2a. So that is equal to, so 1 plus, so look here, so a will be 1, b will be minus b, so minus b, so it is minus b plus or minus, so minus b it will be 1 plus root of 1 square, that is minus 1, it will be taken as 1 minus 1 into minus 1, it is plus 1 minus 4 into 1 into minus 1 divided by 2 into a. So a is 1. So that is equal to 1 plus root of 5 divided by 2. Similarly for R2 we can go with, we will get 1 minus root of 5 divided by 2. So now the roots are distinct. So why the roots are distinct? So one root value will be 1 plus root of 5 by 2, and the second root will be the 1 minus root of 5 divided by 2. So hence the characteristics equation can be further simplified as x of n. X of n you can take, or f of n. So you can use whatever the alphabet you can use. So we can go with the f of n is f of n equal to a into r. So since the roots are distinct, so the equations can be formulated as a into r1 to the power n plus b into r2 to the power n. So here a and b are constants. So therefore, so for substituting with the above equation, f of n equal to a into what is r1, 1 plus root of 5 divided by 2 whole power n plus b into 1 minus root of 5 divided by 2 whole power n. So let this equation be 2. Now we have to obtain the value of a and b. So now we can take the initial conditions. So I have shown you with an example. The first number will be 0. Let us assume the first number to be 0 and the second number to be 1. Okay, so now let us go with the initial conditions. So initially the values we can take with 0 and 1. Let f of 0 equal to 1 and f of 1 equal to 1. So now we have to assume with when n equal to 0. So we have to simplify and we have to find out the value for a and b. So for that we have to go with some substitutions. So when n equal to 0, so the n can be, n is nothing but the input value. So that is the nth number. So what the user is giving for the input. So when n equal to 0, so we can go with two cases, when n equal to 0 and when n equal to 1. So when n equal to 0, so it will be a into 1 plus root of 5 divided by 2 whole power 0 plus b into 1 minus root of 5 divided by 2 into 0. So anything power 0 is always 1. So now a plus b equal to 0. Now when n equal to 1. So when n equal to 1, a into 1 plus root of 5 divided by 2 whole power 1 plus b into 1 minus root 5 divided by 2 whole power 1, that is equal to 1. Okay. So now let us take that equation to be 4. Now what we have to do, so with the equation number 3, we can go with, from 3 we can go with a equal to minus b. So we can go with a equal to, we can substitute instead of a we can go with minus b, else you can go with b equal to minus a. So that's your will and wish. So now I have taken as a equal to minus b. Now we have to substitute the value of a in the equation 4. So when you're substituting the value of a, so now it will be minus b into 1 plus root of 5 divided by 2 plus b into 1 minus root of 5 divided by 2 equal to 1. So now we have to go with more substitutions. So here, so when you're going with substitutions, we are taking b outside. So when you're taking b outside, so it will be 1 minus root 5 divided by 2 minus of 1 plus root 5 divided by 2, that is equal to 1. So now we have taken LCM, that is 2 denominator we have taken common. So 2, so numerator 1 minus root 5 minus 1 minus root 5. So plus 1 minus 1 it will be 0. So here you see plus 1 and minus 1 it will be 0. So now totally it will be b into, so we can go with the second half, b into minus 2 into, that is minus 5 minus root 5 is there. So minus 2 into root 5 divided by 2. So 2 and 2 gets cancelled, that is equal to 1. So now b equal to minus 1 divided by root 5. So now we have got an value for b. So we have taken with the equation number 3 a equal to minus b. So now a equal to, automatically it will be minus into minus of minus 1 by root 5. So automatically it will be 1 by root 5. Now f of n equal to 1 by root 5. So now I have to substitute with the equation. So it will be 1 by root 5 into 1 plus root 5 divided by 2 whole power n minus 1 by root 5 into 1 minus root 5 divided by 2 whole power n. So now we have to assume, so we have to take some assumption here. So let pi equal to 1 plus root 5 divided by 2 and pi inverse to be, let us take as pi inverse equal to 1 minus root 5 divided by 2. Now f of n equal to 1 divided by root 5 into pi of n, pi to the power n minus 1 by root 5 into pi inverse of n. So now we can go with pi. So pi we have taken as assumed as pi equal to 1 plus root 5 divided by 2. So when you're making with the simplifications by using calculator, you'll be getting 1.61803. Now pi inverse, well, that is 1 minus root 5 divided by 2. So when you're calculating with the calculator, you'll be getting minus 0.61803. Now the constant is pi can be called to be golden ratio. So it is a golden ratio. So now finally we'll be getting the equation f of n equal to 1 divided by root 5 into pi of n minus pi inverse of n. So which is approximately equal to 1 divided by root 5 of pi of n. So which belongs to theta of pi of n. So with an approximate negotiating the constants and coefficients, we'll be getting pi of n finally. Okay, is it clear? So now with this, we can go with the conclusion that the time complexity required to generate a Fibonacci of an nth number, it will be order of n or theta of n. Okay, is it clear? So we can go with the next question. So we have solved the first two questions. I think it will be it is helpful for you and it is understandable to you all. Now the second one is to find out the that is time complexity of of a factorial of a n number with respect to a recursive and non-recursive algorithm. For recursive algorithm, we can directly compute with the time and space complexity. We can directly compute. Sorry, for a non-recursive algorithm. Whereas for the recursive algorithm, we have to find out the recurrence relation. We have to solve the recurrence relation, and we have to come up with the time complexity after simplification. Which of the following recurrence relations can be used to define the factorial of a given number? So automatically when you're going with the recurrence so what is a factorial of a given number n? So if it is, for example, so if you have to find out for factorial of number factorial of n equal to 5, so we can represent by means of 5 factorial, that is equal to 5 into 4 into 3 into 2 into 1. So finally you will be getting the answer as 5 into 4 it is 20, 20 into 3 60, 60 into 2 it is 120. Okay. So when it is 1 factorial, so it is 1 alone. Similarly, if it is for 0 factorial, it will go with 1. So now we have to go with the recurrence relation. So what is the basic operation here? It is multiplication. So what is the multiplication here? So f of n into n minus 1. So for example, 5 factorial. So 5 into 4. So 5 into 4 it is 20. Now 20 into 3. So that is 20 into 3. Next, 20 into 3 is 60. 60 into 2. So it is 120. 120 into 1, it is 120. So finally, the factorial of 5 is 120. So now we have to go with how to find out the recurrence relation and the time complexity for the factorial of a given number. So for this, actually, the value will be f of n minus 1 into n. F of n minus 1 into n. That is the first answer is the first option is the correct answer. So now we can see how to derive the recurrence equation for the factorial of n, and how to come up with the time complexity for the factorial for a recurrence relation for a factorial of a given number. So I'll give a stop sharing and we can go with the calculation part. So actually, for factorial using recursion. So what is the recursion? You all know that is, and if an algorithm calls itself again and again for solving a problem, then that type of algorithm is said to be recurrence algorithm. Sorry, recursive algorithm. So it is also known as recurrence algorithm. So you all know. So what is the repeated basic operation here? Multiplication. So n factorial equals 5. It is 4 into 5. So sorry, 4 factorial into 5. So 4 factorial can be further expanded into 3 factorial into 4 into 5. Again 3 factorial can be expanded into 2 factorial into 3 into 4, 5. So the same way it will repeated till 0 factorial into 1 into 2 into 3 into 4 into 5. Now, how to find the algorithm for factorial of n? So it is if n equal to 0, return, sorry, it's 1, return 1. So if n value is 0, it is written 1. Else, return factorial of n minus 1 into n. Now, that is nothing but f of n equal to f of n minus 1 into n, where n is greater than 0. So finally, f of n equal to f of n minus 1 into n. So now we have to find out how to solve by using the recurrence relation. So let it can be taken as f of n or m of n. So both are same. M of n we can take with m. M is nothing but base multiplication. It refers multiplication, since the basic operation for a factorial of a given number is multiplication. So I represented instead of f I am represented by means of m. M of n equal to m of n minus 1 plus 1. So why we are going with n minus 1? So m of n minus 1 is nothing but to compute the factorial of n minus 1. So I have given no. So 5 factorial equal to 4 factorial into 5. Next 3 factorial into 4 into 5. So that is n minus 1. So m of n minus 1 plus 1. So what is n here? To multiply the factorial of n minus 1 by 1 by n. So for that we are in need of time 1 unit. So how to solve this? So we can solve by using backward. You can solve either by using backward substitution or by means of forward substitution technique. So I am going up with backward substitution. So by backward substitution, Let us take m of n. So we already know, let us take that m of n equal to m of n minus 1 plus 1 equal to 1. That is as the first equation. Next equation can be m of n minus 1 equal to m of n minus 2 plus 1. So since here we are substituted for instead of n, we are substituting n minus 1. So in the right side also we can go with n, for instead of n, you are going with n minus 1. So we will be getting m of n minus 2 plus 1. So again, what we have to do is we have to substitute the equation 2 in 1. So while you're substituting, you'll be getting m of n equal to m of n minus 2 plus 2. That is the third equation. So again, you have to apply backward substitution here. M of n minus 2 equal to. So instead of n, you're going with n minus 2. So if m of n minus 2 equal to m of n minus 2 minus 1, that is m of n minus 3 plus 1. Now we have to substitute that equation before. Now we have to substitute the equation 4 in 3. So after that, you will be getting m of n equal to m of n minus 3 plus 3. So similarly, it goes on till I iteration. So you can go up with till the final. So, but intermediately we are going with, if it is for after I iterations, after I number of iterations. So what is the similarity you are getting here? So if it is m of n minus I, if it is ith iteration, so here instead of here n minus 3 plus 3. So what is similarity here? If what is the number which is inside n minus I, that is equal to plus I. So the same value here. So that is a similarity. So we can go with m of n equal to m of n minus I plus I. So if it is intermediately at the ith iteration, if it is a nth iteration, that is the last iteration, that is I equal to n. So if it is I equal to n, then m of n equal to, we have to substitute, instead of I, we have to substitute n. So m of n minus n plus n equal to, so what is n minus n? It is n minus n, it is 0. So m of 0 plus n. So what is 0 here represents if the value of n is equal to 0. So if the value of n equal to 0, it is 0 factorial. So if it is 0 factorial is equal to 1. So 1 plus n. So 1 plus n after negation, after eliminating the eliminating the coefficients and the constants. So you'll be getting n. So finally we can come up with the time complexity equal to order of n. I hope you have understood all this. So we can also find out whether this time complexity what we have applied here is correct or not. So for that you can use mathematical induction. Say mathematical induction. So we are just to substitute and see it. So if n equal to 0 and n equal to n minus 1. So if n equal to 0, then m of n equal to 0. Then m of 0 equal to 0, that is equal to n. Similarly for induction, if it is n equal to n minus 1, so substitute for the front and left side and right side of the equation. So m of n minus 1 equal to n minus 1. So now we are substituting for, instead of n, you are substituting n minus 1. So m of n equal to m of n minus 1 plus 1. Minus 1 plus 1 gets cancelled, that is equal to n. So this is, so after deriving the equation, is a time complexity for the recurrence equation, you can check it out whether what you have derived, the equation what you have derived is correct or not. So to prove the correctness of the solution what you have derived, you can apply mathematical induction and find out whether it is correct or not. I hope you have understood how the recurrence equation for a Fibonacci and a factorial of a given number has been derived by using. So we have taken two problems here. So the problem number 1 is Fibonacci and the problem number 2 is factorial of a given number. So I'll repeat once again. So for the recurrence equations for a Fibonacci of a given number n, so what is the answer is f of n equal to f of n minus 1 plus f of n minus 2. Similarly, for the factorial of a given number, it is, the option is A, that is f of n equal to f of n minus 1 plus n into n. So I hope you have enjoyed the session and you have understood how to derive a recurrence relation for a given problem. So the procedure to find out the time complexity for a given problem for a recursive, in a recursive manner is, the first step what you have to do is, so you have to analyze the problem first. Second, you have to derive the recurrence relation for the given problem. So next, you have to use the either backward substitution or forward substitution, or the one more method is a master's theorem. So you can apply any of these methods to simplify or to find out the time complexity for the given problem. So unless the recurrence relation what you have derived, what you have generated is correct, the time complexity you'll derive will be correct. Okay, I hope you have understood the problems, both the problems. So thank you for patience listening. And for the next, we can go with the next type of recurrence relation in the forthcoming presentation. Thank you.